Rust in AI Masterclass by Edgar Milvis Volume 1, Chapter 4. Now, let's explore Chapter 4, Stack versus Heap, the impact on inference latency. Turning our attention to theoretical foundations. To understand why memory management is a critical performance lever in AI inference, we must look beyond simple allocation and deallocation. We need to analyze the physical and logical structure of memory as it pertains to the CPU's execution pipeline. In the context of loading large language models, LLMs, or processing high-dimensional tensors, the distinction between the stack and the heap is not merely a matter of scope or lifetime, it is a fundamental determinant of instruction throughput and latency. Moving on to the physical reality, proximity and access patterns. At the hardware level, the CPU does not access memory uniformly. It operates through a hierarchy of caches, L1, L2, L3, that sit between the registers and the main RAM. Accessing data in L1 cache is orders of magnitude faster than accessing data in main memory. This speed difference is the primary driver of latency in modern computing. The stack, the fast lane. The stack is a contiguous block of memory allocated at the start of a thread. It grows and shrinks strictly in a last-in first-out (LIFO) manner. Because the stack is always contiguous and its size is known at compile time, or thread creation, the CPU can predict its location and layout with high precision. Analogy: imagine a stack of plates in a cafeteria. You can only place a plate on top or remove one from the top. Because the plates are stacked vertically in a single column, accessing the top plate requires no searching, you simply extend your arm to a known height. This is analogous to the CPU's stack pointer, RSP on x86-64, which points directly to the top of the stack. Accessing stack variables is essentially free in terms of latency because the data is almost always hot in the L1 cache. The heap, the warehouse. The heap is a large pool of memory available for dynamic allocation. Unlike the stack, heap allocations can happen in any order and live for arbitrary durations. When you allocate memory on the heap, the allocator searches for a free block of the requested size. Over time, as blocks are allocated and freed, the heap becomes fragmented, scattered with used blocks and holes of varying sizes. Analogy: the heap is like a massive, disorganized warehouse. When you request a specific size of storage, e.g., 100 square feet, the warehouse manager, the allocator, must walk through the aisles to find a suitable empty space. If the warehouse is fragmented, filled with small, scattered items, the manager may have to walk a long distance to find a gap that fits your request. Furthermore, the data you store might end up in a completely different aisle from related data, breaking spatial locality. Let's discuss the inference bottleneck, cache misses and branch misprediction. In AI inference, we execute matrix multiplications and activation functions repeatedly. These operations are memory-bound, meaning the CPU spends more time waiting for data to arrive from memory than it spends actually computing. When data resides on the stack, the CPU prefetcher can often anticipate the access pattern, e.g., iterating through a small buffer of weights, and keep the data in the L1 cache. However, when data is scattered across the heap due to fragmented allocation, accessing a single element might trigger a cache miss. The CPU must stall execution while fetching that data from L3 cache or, worse, main RAM. The double indirection problem in Rust, heap allocation is often abstracted via pointers. Consider accessing a field in a struct allocated on the heap. 1. The CPU loads the pointer address, register or L1 cache. 2. The CPU dereferences the pointer to find the base address of the struct, potential L1 miss. 3. The CPU calculates the offset to the specific field, e.g., offset 16 bytes. 4. The CPU loads the field value, potential L1 miss. If the struct contains pointers to other heap allocated data, common in complex AI model graphs, this indirection chain multiplies. This is the pointer chasing problem. In contrast, a stack allocated struct is accessed directly via the stack pointer plus an offset, often requiring only one memory access. Turning our attention to smart pointers, managing heap latency with safety. Rust provides smart pointers, boxt, RCT, arct, to manage heap memory safely. While they incur the latency penalties of heap allocation, they offer deterministic lifetimes, which is crucial for managing large models that cannot fit on the stack. The cost of ARC, atomic reference counting, arct allows multiple parts of the program to own the same heap data. It uses atomic operations to update a reference count. While thread-safe, atomic operations are slower than non-atomic ones because they require synchronization across CPU cores to prevent data races. Systems analogy, file locking. Think of ARC mutex as a library checkout system for a rare book, the data. ARC, reference counting. This is the checkout ledger. Every time someone borrows the book, the librarian increments the count. When they return it, the count decrements. When the count hits 0, the book is shelved, deallocated. Mutex, mutual exclusion. This is the lock on the book's cover. Only one person can write in the book at a time. The latency impact: just as a librarian takes time to update the ledger and check the lock, the CPU takes time to increment/decrement the atomic reference count and acquire the mutex. In high-frequency inference loops, the overhead of checking out the book repeatedly can dominate the actual reading time. Box T single ownership. Box T is the simplest heap allocation. It has no reference counting overhead. It is akin to placing an item in a secure locker that only you have the key to. The latency cost is strictly the initial allocation and the indirection of accessing the data. Moving on to custom allocators, defeating fragmentation. Standard global allocators, like malloc in C or the allocator behind Rust's std alloca system, are general purpose. They handle requests of all sizes, which inevitably leads to fragmentation. For AI inference, where we often allocate many tensors of similar sizes, e.g., batches of inputs, and then free them, a custom allocator is superior. The bump allocator strategy. A common strategy for inference is a bump or arena allocator. 1. Pre-allocation. At the start of an inference run, we allocate a large contiguous block of memory, an arena, on the heap. 2. Linear allocation. During inference, we simply move a pointer forward, bump, to allocate new tensors. There is no search for free blocks. 3. Deallocation. We do not free individual tensors. We free the entire arena at the end of the inference run. Analogy: this is like renting a banquet hall for a wedding. You don't rent individual tables by the minute, you rent the whole space. Guests, tensors, come and go, but you don't worry about cleaning up individual spots until the event is over. This eliminates the fragmentation overhead entirely. Now, let's talk about optimizing memory layout, cache locality. Even with heap allocation, we can optimize for latency by controlling how data is laid out in memory. This concept, introduced in previous chapters regarding data structures, is vital here. Structure of arrays, SOA, versus array of structures, AUS. In AI, we often process vectors or matrices. AUS, storing a struct point, x, f32, y, f32, z, f32, in an array means memory looks like x1, y1, z1, x2, y2, z2. If you only need to process x values, you still load y and z into the cache, wasting bandwidth. SOA, storing three separate arrays xs, vec-f32, y's, vec-f32, z's, vec-f32 means memory looks like x1, x2, y1, y2. When processing x, the cache is filled only with relevant data. Visualizing the impact on cache lines, a standard cache line is 64 bytes. In an SOA layout, loading one f32 for bytes brings in 15 neighboring f32s that are likely used in the same calculation, e.g., a vector dot product. In an AUS layout, loading x1 brings in y1 and z1, but if the next calculation is x2, y1 and z1 become cache evictors. In an array of structures, AUS layout, loading x1 also fetches y1 and z1 into the cache, but subsequent calculations for x2 may cause y1 and z1 to be evicted before they are used, leading to inefficient cache utilization. Now, let's talk about the role of the borrow checker in latency optimization. Rust's borrow checker is not just a safety feature, it is a layout enforcer. By enforcing that you cannot have mutable references to data while you have immutable references, it prevents the need for runtime locking mechanisms, like mutex, in single-threaded contexts. Analogy: the resource manager. Imagine a construction site, the program, with a single crane, the CPU. The borrow checker is the site manager. Mutable borrow, and mut-t, I need exclusive access to the crane to move this heavy beam. The manager ensures no one else uses the crane. Immutable borrow, and t, I need to look at the blueprints. Multiple workers can look at the same blueprints simultaneously. Latency impact: if the manager, borrow checker, can verify these rules at compile time, the workers, CPU instructions, don't have to stop and ask for permission, runtime locks, at every step. This eliminates synchronization overhead, allowing the CPU to execute instructions linearly without stalling. In the context of AI inference, latency is dictated by 1. Allocation speed, stack bump allocator general heap allocator. 2. Access pattern, contiguous, stack/SOA, scattered, fragmented heap/AUS. 3. Indirection, direct, stack, pointer chasing, heap graphs. For synchronization, lock-free, borrow checker, atomic, arc/mutex. By understanding these theoretical foundations, we can design memory layouts that align with the physical constraints of the CPU, turning theoretical flops into actual throughput. Let's discuss basic code example. To understand the performance implications of memory allocation in high-performance AI systems, we will model a simplified inference pipeline. This pipeline processes a batch of input data, applies a transformation, simulating a neural network layer, and outputs the result. In this context, stack allocation is used for fixed size, short-lived metadata, e.g., dimensions, loop counters. It is extremely fast but limited in size. Heap allocation is used for dynamic data structures like vectors of input data or model weights. While flexible, it incurs allocation/deallocation costs and can lead to cache misses if not managed carefully. We will demonstrate two versions of the same logic. One, naive approach, relies heavily on the heap and standard idioms, which can introduce latency. 2. Optimized approach, uses stack-allocated arrays, fixed size, where possible and smart pointers, ARC, for shared data to avoid unnecessary deep copies. Now, let's talk about the Rust code. Notice how we import instant for precise timing and rand_RNG for generating random weights. At line 12, we define hidden_size as a constant, which is crucial for stack allocation. This architectural choice forces a fixed tensor size, enabling high-speed stack access but limiting flexibility. In production, this would be a trade-off. Stack allocation avoids heap fragmentation and allocation latency, but for variable-sized models, you'd need dynamic allocation, which could impact performance in tight loops. See how the inference layer struct holds weights and bias on the heap using vec_f32. We choose vec for dynamic sizing, but note that in a real model, these could be gigabytes. Using vec allows efficient memory management, but without smart pointers, cloning would be expensive. This connects to the ARC usage later. We share ownership to avoid deep copies during inference. If we used raw pointers, we'd risk memory leaks. Vec with ARC provides safe, shared access. Look at the new method where weights are allocated on the heap via collect. This happens once during initialization, which is fine, but in training loops, frequent reallocation would be costly. We use rand_thread_RNG for speed, but in multi-threaded contexts, you might need a seeded RNG for reproducibility. The implication, heap allocation here is acceptable because it's outside the critical inference path. If done inside a loop, it would cause significant latency. Observe the forward method signature. It takes a stack allocated array slice and f32 hidden_size. This is key for performance. Stack access is faster than heap. At line 53, we pre-allocate the output vec on the heap, which is necessary because output size varies. We could reuse this buffer, but the method returns ownership, so in a loop, you'd want to pass a mutable buffer in. Without this, each call would allocate, hurting scalability in batch processing. See the matrix multiplication loop. We access self.weights, heap, and input, stack. The linear indexing, I*input_size plus j, is efficient but assumes row major order. Using a crate-like array would handle stride safely. The ReLU activation at line 67 is simple but critical for neural networks. If we used a more complex activation, it might add overhead. In production, this loop is the hot path. Optimizing it with SIMD or GPU offload would be essential for large models. Notice the naive_pipeline function. It takes a vec of inputs and returns a vec of outputs. This is common in beginner code but introduces cloning overhead. At line 82, layer.forward and input works because input is borrowed, but if we needed ownership, we'd clone. The implication, for large batches, this approach wastes memory and time. In real-world scenarios, this could lead to OOM errors in Kubernetes pods with limited memory. We avoid this in the optimized version by reusing buffers. Look at the optimized_pipeline. We use std sync ARC inference layer to share the layer without cloning weights. This is a best practice for read-heavy workloads like inference. At line 92, vec with _capacity pre-allocates results, reducing reallocations. The reusable buffer at line 97 is a heap-allocated scratchpad. This minimizes allocations inside the loop. Without this, each forward pass would allocate a new vec, causing fragmentation and latency spikes in production. See the loop where we reset the reusable buffer at lines 102 to 105. This is manual but efficient. In Rust, you could use iter_mut.for_h x *x equals 0.0 for clarity. The forward pass logic mirrors the forward method but writes directly to the buffer, avoiding extra allocations. At line 121, we clone the buffer for storage. This is a trade-off. Cloning is cheaper than reallocating, but in a zero-copy design, you'd swap buffers or use a ring buffer. This connects to memory efficiency in large-scale inference. Observe that we clone the buffer for each result. This is necessary because the buffer is reused, but it adds some overhead. In a highly optimized system, you might use a pool of buffers or unsafe code to avoid cloning. The implication, for very large outputs, cloning could still be costly. We choose this over unsafe code for safety, but in performance-critical paths, developers might opt for unsafe with careful auditing. This highlights Rust's balance between safety and speed. In main, we set up the layer and data. At line 129, inference layer and new allocates weights on the heap, which is fine for initialization. Wrapping it in arc at line 131 enables shared ownership across pipelines. The batch generation at lines 137 to 145 uses stack allocated arrays, which is efficient for input data. Notice we generate random inputs, this simulates real data loading. In production, this might come from a data loader with shuffling and augmentation, affecting latency. See the timing setup, we use instant to measure latency, which is crucial for performance analysis. At line 154, we call naive_pipeline with inputs.clone, which clones the entire batch. This is the bottleneck we're comparing. The naive pipeline's duration is printed, showing the cost of allocations and cloning. In a real system, this could be 10x slower than optimized, impacting throughput in serving models to users. Look at the optimized pipeline run, we pass layer_arc.clone, which is cheap because arc increments a reference count. The inputs are moved, avoiding a clone here. The timing shows the improvement from buffer reuse and shared ownership. At line 161, we measure elapsed time. This is where the architectural choices pay off. In Kubernetes, reduced latency means better resource utilization and lower costs. Finally, we compute the speedup factor and print insights. At line 166, the factor quantifies the benefit of optimization. The note at line 167 emphasizes minimizing heap allocations, which is key for scalability. Without this, the naive version could exhaust memory in large batches. This connects to the book's themes. Mastering lifetimes and smart pointers enables efficient memory patterns for AI models, where datasets are massive and latency is critical. By scanning this code, you go on the details on leanpub.com. By scanning this code, you go on the details on amazon.com. This code bring you to the source code repo on github.com. Thank you for your attention. This lesson is excerpted from Volume 1, Chapter 4 of the Rust in AI Masterclass ebook series and from the volume Advanced Memory Patterns for AI. You can find all the details here, https://github.com/edgarmilvis/rustai programming series. The ebook also includes 20 chapters with diagrams, advanced examples, and 5 exercises with solutions. I look forward to seeing you in the next lesson.